Hello everyone, and welcome to Lesson 8 of our Python programming course. Today, we're diving into one of the most important topics for any serious programmer: testing, debugging, exceptions, and assertions. This is where we move beyond just writing code. We learn how to make it robust, reliable, and professional. By the end of this lesson, you'll understand how to systematically find and fix errors, how to handle unexpected situations gracefully, and how to write code that defends itself against mistakes. Before we even start testing or debugging, we need to set ourselves up for success. That means 3 key things. First, write clear specifications for your functions. What does the function promise to do? What inputs does it expect, and what will it return? Second, modularize your programs. Break your code into small independent pieces, functions, or classes that you can test and debug in isolation. And third, check conditions on inputs and outputs using something called assertions. We'll come back to assertions later, but think of them as built-in sanity checks for your code. Now, what's the difference between testing and debugging? Testing is about asking, is my program working according to the specification? You compare input-output pairs and try to break your program on purpose. Debugging is what happens after a test fails. You ask, why is it not working? And how can I fix it? It's detective work, tracing back from the error to find the root cause. So how do we make testing and debugging easier? We design for it from the very beginning. Break your program into testable modules. Each function should do one thing well. Document constraints. What inputs do you expect? What should the output look like? Document your assumptions. Why did you design it this way? What edge cases are you considering? Good documentation isn't just for others, it's for your future self when you come back to the code in 6 months. You're ready to test when 2 things are true. First, your code runs without syntax or static semantic errors. Python's interpreter will catch many of these for you, like missing colons or undefined variables. Second, you have a set of expected results. That means, for a given set of inputs, you know what the output should be. If you don't know what the right answer is, how can you test if your code found it? There are 3 main types of testing you should know. Unit testing, testing each function or module individually. This is where you validate every small piece of your program. Regression testing. Every time you find a bug, you add a test for it. Why? To make sure the same bug doesn't reappear later after you've fixed it. This is how mature software projects stay stable. Integration testing. Once units work, you test the whole program together. Do all the pieces connect correctly? Does the overall system meet the requirements? Many students rush to integration testing too soon. Don't skip unit tests. Now, how do we actually design test cases? One way is to use intuition about natural boundaries. For example, if you have a function is bigger, x, y, that compares 2 integers, you might test x bigger than y bigger than xx equal to y. Those are natural partitions of the input space. If there are no obvious partitions, you might try random testing. Just try lots of inputs and see if anything breaks. But there are better, more systematic approaches. Black box testing. Exploring paths through the specification without looking at the code. Glass box testing. Exploring paths through the actual code. Let's look at black box testing with an example, a square root function. We have a specification, sqrt x eps assumes x federate 0 eps 0 and returns a result such that x eps termes result term x plus eps. In black box testing, we ignore the implementation. We only look at the spec and ask, what are interesting values to test? This can be done by someone other than the coder, which helps avoid bias. And if the implementation changes, the same tests still apply because the spec hasn't changed. We think about boundary conditions, x trouwens 0, very small EPs, different categories, perfect squares, irrationals, very large numbers. Here's a test table for a sqrt boundary, x0, EPs, box 0 or 01, perfect square, x0 25, less than 1, x for 0 5, irrational, x for 2. Extreme values, very tiny or huge numbers for x and eps. Testing extremes is critical. They often reveal hidden overflow or precision bugs. Now, glass box testing is different. Here we look at the code to guide our tests. We aim for path-complete testing. Every possible path through the code is tested at least once. But there's a catch: loops. A loop can run 0 times, 1 time, or many times. Testing all possibilities can be impossible if the loop runs based on input. Guidelines for glass box testing: test all conditional branches. For loops, test not entering, entering once, entering multiple times for while loops. Test all ways to exit the loop. Consider a flawed function intended to return the absolute value of an integer. The code checks if the input x is less than -1. If so, it returns -x. Otherwise, it returns x. A tester aiming for path completeness might see 2 paths, one where the if condition is true and one where it is false. They might test with x inverse 2 and x inverse 2. Both tests would pass, suggesting the function is correct, but a bug remains. What is the absolute value of -1? According to this function, it would be -1, which is incorrect. The bug exists at the boundary condition, x⁻1, which our path complete suite missed because it didn't consider boundary values within a path. This illustrates a vital lesson. Even with glass box testing, you must still think critically about edge cases and boundary values within the data, not just the code paths. Debugging can present a steep learning curve. The ultimate goal is a bug-free program, or at least one where known bugs are understood and managed. To achieve this, we use both tools and methodology. Python provides several helpful tools. Integrated development environments like Idle and Anaconda have built-in debuggers that allow you to step through code, inspect variables, and control execution. Online tools like Python Tutor can visualize execution step by step. Sometimes the most effective and accessible tool is the simple print statement. Strategic placement of print statements can reveal the program's state at critical points. However, the most important tool is your own systematic reasoning. You must be a detective, forming hypotheses and gathering evidence methodically. Let's discuss how to use print statements effectively in debugging. You should print key information at function boundaries, print the parameters as the function begins, and print the return value before it ends. This confirms the function is being called with the data you expect and is producing the output you intend. A powerful technique is the bisection method. When you are unsure where a bug lies, place a print statement roughly halfway through the relevant section of code. Examine the output. Does the program state look correct at that midpoint? If so, the bug likely lies in the second half. If not, it lies in the first half. You then repeat this process, narrowing down the location of the bug by half each time, much like a binary search. Effective debugging mirrors the scientific method. When you encounter an unexpected result, your first question should not be the vague "what's wrong?" Instead, ask a more precise, data-driven question. How did the program arrive at this unexpected result? Investigate if this bug is part of a family of similar errors. Is there a pattern? Then apply the scientific process. First, study all available data, error messages, printed variable values, and program outputs. Second, form a specific testable hypothesis. For example, I hypothesize that the loop index I is exceeding the list length by 1. Third, design and run a repeatable experiment to test this hypothesis, ideally using the simplest possible input that reproduces the bug. Finally, analyze the results, refine your hypothesis, and repeat. In your debugging work, you will frequently encounter specific exceptions raised by Python. Let's review some of the most common ones. An index error occurs when you try to access a list element using an index that is outside the valid range for that list. For example, accessing the 5th element of a 3-item list. A type error can occur in several contexts, such as attempting to convert a non-numeric string or a list to an integer using the int_on function. A name error happens when your code references a variable name that has not been defined in the current scope. Another form of type error occurs with inappropriate operations between types, such as attempting to divide a string by a number. Finally, syntax errors are caught before the program runs and typically involve structural mistakes like missing closing parentheses or quotation marks.